So what you just did right now, again, I tell you things that I think are really important. I'm telling you not to waste your time, because I know that your time is really, really tight. I'm telling you because this is actually going to save you time. So doing something by hand first with numbers and seeing how it works and why it works, it knocks out so many other problems. Some of us sat outside of class for Dr. Forgaston's class when you were doing numerics, and we just did a couple steps by hand. Maria, you were there for that, right? Where we did a couple steps by hand. It like, oh, right, all of a sudden, as you did it by hand, you're like, oh, now I totally understand what's going on, and the problems get knocked out. Not just that one problem, but any problem that comes at you gets knocked out. So that's why it's important to work something with your hands first and know what it works, why it works for numbers before you go over and try to solve the problem. I know, but busy people think I have to solve the problem, and the best way to solve the problem is to do the problem immediately. But you can spend all your time floundering around, and you'll end up spending your time floundering around longer than the person who actually did a little front end work first. I promise. I saw a little light in your eyes. She knows what I'm thinking. I told you I've been there before. So why? I actually thought it was interesting that this individual on YouTube was talking about congruences and backing up a little bit and trying to make it real for the person who's listening. So I want to borrow what he did to show you what congruences are actually, why you get that family of solutions. Now, we also call working with mods clock arithmetic, and especially when we explain it to younger students. So if you are considering teaching middle school, that's one place where they'll talk about clock arithmetic, because they're trying to engage students in other kinds of math. The idea of math, I guess at that level, is just to get them engaged and start to think like in a math way. So why do they call this clock arithmetic? And you can't see my writing at the top, but the reason is because you want to think of a clock that only has a minute hand. Well, when it has a minute hand and it's rotating around, and let's say it was at 11 minutes in this clock that I've drawn, you would not be able to tell the difference between 11 minutes or 71 minutes or 131 minutes. They're all the same. So all those numbers, 11, 71, and 131, are really in the same family. So every time I rotate by 60 minutes, I'm just going to get the same place. So that clock will look identical to me. I wouldn't be able to tell you the difference. So that means that if I took that clock and swung it around several times, and you were not in the room, and then you walked in the room, and I asked you, what number is that? You might say 11, because 11 maybe represents all of them. But then what if you said 11, I said, ha-ha! It's actually 131. You'd say, that's unfair. Yeah, wasn't here when you rotated that around. How am I supposed to know? That's really a family of solutions. So all of them are in one box with the number 11 on the outside. So that's the reason we think of this as a family of solutions. I don't know if that helps a little bit. That's why we really look at it as a whole family of solutions that are, the entire box represents the solution to the equation. And how we write it formulaically, so it's really easy to understand when you have the clock in the picture, but how we write it formulaically is we'd say 11 plus any multiple of 60. And you've already done this with the unit circle, I know, because I'm teaching pre-calc right now, right? You think of rotating around many times as being the same thing. So they all look the same, so you wouldn't be able to distinguish between 11 and 71, for example. So we collect all that information, and instead of saying 11, 71, 131, ... we compress it into x is congruent to 11 mod 6. That's how we put them all into one box. That's how we express that family. It's not equals, right? Equals implies there's one number. It's really that it's the whole box is there. That's why we have the 3 hash marks. Clear? By the way, I've seen problems like this on my son's NJ Ask, so that's why I said I know that they're there. I know it's taught at some level, either in elementary school or middle school. So if you're interested in teaching, even if you're not interested, I'm sitting on the board of ed, so I can tell you that they'll move people around. So you may have thought, well, I'm going to be teaching sophomore level math, and then all of a sudden you'll be in 7th grade. They can move you into 7th grade. So you might be actually looking at this not too far into the future. I feel like I've helped people with the praxis before, and I feel like I've seen problems like this on the praxis too, where a little bit tougher than this, where they give you something where they tell you some information and it's on a clock, and you have to back calculate off the clock to figure out the answer. So I feel like I've seen this before on the praxis as well. Anybody studying for the praxis? Did you see anything in your books like this? It's been a few years, but I just have a feeling that I've seen it before on the praxis study books. So I have seen that. So another problem that I think he showed is these problems that, and I've seen these before for young kids, and math Olympiads. So when you're teaching, or when you're doing your methods class, I don't know who you're targeting at, but maybe they target you at the middle, the average student, or do they target you at, oh, what will happen when we get to really tough students that need help? Do they ever tell you about the really smart students? They get stuff like this. And they can move you around for that too. I've seen them do that. So they'll take a teacher's in the regular 5th grade classroom and then move him or her to the gifted and talented. And then you just have to do these problems. So they're there. So how do you solve something like that? Well, can't see that because it's scroll down. Let me see if there's a way. You can see it now. Yeah, it is. It's irritating. So I'm going to show you 2 ways to solve this. I'm going to show you the number theory style way to solve it first. And it's going to be so complicated. But then I'm going to show you how I showed my son and his Math Olympiad team. Because I can't show them the stuff I'm showing you here because they're not into symbolic manipulation yet. So how do you do this problem if you did it number theory style? Well, really what you're looking for is you're looking for a congruence equation to solve. So the first step of the first strategy to do this is to set up a congruence equation that's mod 7. The reason mod 7 is because we're dividing by 7. So that tells you that I have to do it mod 7. And I want to find a nice, easy number to put there so that I can get this congruence equation to work. Anything will work. So I put 2 there because it was the simplest thing that'll work. So that's just the map method. Just go through and just check a few and just plug it in there. That works. So just like the previous exercise that I just showed you, you're just looking for a divisor of 16 that's congruent to 1 mod 7. I've shown you something like this from Underwood-Dudley. So that's the second step. So do you remember a problem I showed you where I had a congruence to solve and I couldn't cancel out of both sides because the theorem didn't apply there? And so I thought of another congruence equation that was that looked like it was unrelated, and then I used it to fuse it into the first one. So that's the trick I'm using now. So step 2, like a previous exercise that we did for Underwood-Dudley, try to find a divisor of 16 that's congruent to 1 mod 7. If you recall, then that problem, I had a 1 floating around, so it made the merging of them easy. So 8 is congruent to 1 mod 7. That's the easiest thing I can think of that's congruent to 1 mod 7. So now I have these 2 bits from step 1 and 2. I have 16 is congruent to 2 mod 7 and 8 is congruent to 1 mod 7. Those are my 2 ingredients to find the solution number theory style. Ugh. So the next step I'm going to do is raise the 16 and the 2 to the 47th power. The reason I'm going to do that is because I have to work with 16 to the 47th power. And that what allows me to do that? Well, I'm allowed to multiply both sides by the same thing, so I'm allowed to do this. And that's property E on page 29 of Underwood-Dudley. Now I'm going to take the boxed information at the top that's cut off and the boxed information below, and use the boxed information at the top to replace it inside this boxed information below. How do I do that? Well, I'm going to express the 16 as a bunch of 8s, and I'm going to express the other side as a bunch of 8s as well. I'm going to factor out a 2 cubed. So 2 cubed is 1 mod 7, so I'm just going to I'm allowed to actually replace that 2 cubed with a 1. So that's the theorem that allows me to do that. So I have this mess right here below. So all I'm doing is taking that 2 cubed, because 2 cubed is congruent to 1. They're in the same box. That's what it means, right? So I can replace the 2 cubed with the 1. But 1 to any power is, as far as I know, that one still holds. It's still 1. So I get 2 cubed times 2 to the 47th is equal to, or congruent to 4 mod 7. So if I work the math out, I get 2 to the 47th is congruent to 4 mod 7. And it turns out that when I've worked it down this low, that number that I get there is the remainder. No child can do this. I mean, some child can do this, but not my child can't do this at age 5th grade. He probably still can't do this, and he's a freshman. So that's how you find it. Those are the systematic steps, number theory style, to go and find these remainder problems. And these remainder problems, you see them all the time given to students who are ahead, at least at the elementary school level. I've seen them so many times. Every time I saw them, I went, number theory, this is a number theory problem. So the way I showed him was different. How did I show my son? He was not in 5th grade. He was in 3rd grade when they were showing him this. Can you imagine? 3rd grade. I love my district, but we're actually probably upper middle for the ranking, NJ rankings. So it's not like we have a bunch of geniuses floating around the place. It's we're pretty average in some ways. So you can expect to see something like this. Here's how I showed him. I asked him to look for patterns. Look at 16 to the start raising 16 to a power, and then divide that answer by 7. And find the remainder. Now he's in 3rd grade, so dividing things is a pretty good exercise for him, so it teaches him long division, and he can get the remainder and put it in. Make a table. So I'm of course lazy. I don't want to do this. I just went on Excel and calculated the remainders. So I see something. I had him do this, 2, 4, 1, 2, 4, and then I'd say, guess what the next one's going to be. 1. So it's not that tough. So it looks like the remainders are always cycling 2, 4, 1. And they should, right? Because we're working with a congruence equation, and each one of the things are put into boxes, and everything's got to be in one box. And it looks like there's 3 boxes. One has a label 2, one has a label 4, and one has a label 1. So it repeats every 3 cycles, 2, 4, 1, 2, 4, 1. So if I kept going down the list, where does 47 fall in that round? Well, 47 has a remainder of 2, so it's in the second of the triplet. So it must be 4. Same problem, just work with numbers, not using algebraic formulas. So which one do you guys like? The Ajay style or the number theory style? Like the Ajay style?
That's right. We change it to base 2. It's actually
Yeah, that's what we did in the number theory style, right? We changed it to base.
You could also change this into base 2.
Yeah, you could, but again, I think you'd have. This is not the only problem he has. It's like 6 of them every week, and he's in 3rd grade. And in 3rd grade, they're thinking, "I'm at the top of the game. I'm the smartest in the class. I was chosen for this thing." So now you're asking him to sit down and think really hard. We had a few wars in the house, and the other parents, forget it. They came to my house. So everybody came to my house so they could sit there, because not every parent does math. So yeah, they could change. But yeah, every time I targeted this at my son and his friends, I was thinking, what is the minimal information I have to show them to get them to start experimenting numerically? So that was and I did try to use algebra, because algebra is such a powerful tool, but they couldn't do it. It was too much.